where inductively coupled plasma has many advantages. Okay, this list are the virtues of inductively coupled plasma. First, this technique eliminates many common interferences. Uh, why? Because the flame temperature is really hot. The plasma temperature is really hot. Yeah? Here, the plasma is twice as hot as a conventional flame, and the residence time of light in the plasma is about twice as long. Okay, so temperature is much higher, and also residence time is higher. So that makes uh, the the many common interferences eliminated. Okay, and atomization is more complete and signal is enhanced. Okay, yeah, more atomization is done in the plasma. Okay, and formation of analyte oxides and hydroxide is negligible. Okay, yeah, oxides and hydroxides are not complete atomization. Okay, so, but in inductively coupled plasma, those formation of oxides and hydroxides are negligible. Okay, and the plasma is remarkably free of background radiation. Okay, because this is not a flame. Flame itself, flame itself makes background radiation, but this plasma uh, is free of background radiation. Okay, and in a plasma, the temperature is more uniform. Okay, you see the flame. Flame temperatures quite depend on the location of the flame, but here plasma temperature is more uniform and self-absorption is not nearly so important. You see here, what is the self-absorption? Yeah, self-absorption is emission from the central region is absorbed in in the outer region. Okay, it appears in a flame spectroscopy. Okay, but in a plasma, self-absorption is not nearly so important. And also, plasma emission calibration curves are linear over 5 orders of magnitude. Okay, so the linear range is 5 orders of magnitude. Yeah, is quite a wide range, right? And so this table compares the atomic analysis method, yeah, flame absorption, furnace absorption, plasma emission, and plasma mass spectrometry. Okay, the most sensitive technique is plasma mass spectrometry, and you will see soon. And uh, usually the emission is more sensitive than the absorption, but here furnace absorption, you know, inside the furnace, yeah, graphite furnace, the residence time is higher. Yeah, it's more sensitive than flame absorption and plasma emission. Okay, linear range for the absorption spectroscopy is quite low, uh, only 2 orders of magnitude. But for plasma emission, ICP is 5 orders of magnitude. We can only secure the linear range. But the plasma mass spectrometry, linear range is 8 orders of magnitude. Yeah, okay. Also, detection limit is quite low. Extremely sensitive. Okay. So precision is also well, they are not very different. Okay. And interference, spectral chemical mass, and let me see. For example, the plasma absorption spectroscopy, spectral interference is very few, but the chemical interferences are many. Okay, and let me see. Uh, yeah, and in this case also, plasma mass spectrometry is best. Okay, and sample throughput is which one? The plasma mass spectrometry is the best one. Okay, and then plasma emission, and then flame absorption, then furnace absorption. Okay, dissolved solid here. Uh, let me see. furnace absorption, it is solved solid is higher. Yeah? But in a plasma mass spectrometry, this it has a very low percentage. Okay, and sample volume. Yeah, you need a large sample, large volume of sample for flame absorption. Okay, but the furnace absorption, since you put a very small sample in the furnace, so you don't need in a large volume. Okay, for flame also emission and plasma emission and plasma mass spectrometry, the sample volume is a medium. Okay, and purchase yeah, cost is the most expensive for plasma mass spectrometry. Okay, and flame absorption is the cheapest. Okay, the next topic is sampling by laser ablation. Okay, in this case you need pulsed laser of a very high intensity. Okay, this pulsed laser is focused onto a microscopic spot. Here, microscopic. So in a very small area, laser beam is focused. So laser beam is so intense, so that the focused spot, sample, here, for example, this is an image after laser ablation. This part will be, atomized, evaporated from the surface. Okay, the explosion of particles, atoms, electrons, and ions into the gas phase. Okay, yeah. Why? Because laser beam, laser energy is focused in a very small area. Right? Look at that. This is this is around 40 micrometers wide, so very small spot. Okay, and which laser is commonly used? Neodymium, YAG laser. YAG means this neodymium, doped yttrium, and aluminum garnet. Okay, that's the so-called ND YAG laser. Okay, with a wavelength of 1.064 micrometer. This is near IR range is used. 10 nanosecond pulse. Wow, very short pulse. Okay, with 10 millijoule of energy. Actually, 10 millijoule is not much energy, but this energy is focused very during the very short time. Okay, and then in this small spot, a lot of energy is focused. Yeah, so that's why the surface is mm, damaged. Okay. Okay, and 10 millijoule of energy focused on the spot diameter of 50 micrometer. And maybe this is about 50 micrometers. Delivers a power of, look at that. Yeah, in terms of power per unit, the area is 50 gigawatt. Okay? Can you imagine this much of power? 50 gigawatt. Although energy is very low, but in terms of power, it is in extremely high power. Okay, so under this power, material is typically removed to a depth of 0.0225 micrometers by each pulse. Okay, here. This part is just mostly surface is, some surface is removed. Okay, yeah. This is a microscopic crater. The crater. Yeah, you see from the telescope the moon has many craters because of the collision from the outer space. Yeah, the microscopic crater oblated into a mussel shell by 10 pulses from 266 nanometer laser with a beam energy of 4.5 millijoule per 10 nanosecond pulse. And the repetition rate is of 10 hertz. Okay, so 10 pulses. Okay, to have 10 pulses with 10 hertz, how many seconds is needed? Only 1 second. Okay, 1 second, just 1 second. 10 pulses are focused on this small spot. Okay, and then here atomization, all kinds of things happen. Okay, atoms, electrons, and ions are produced. Okay, and then that produced one is detected by atomic maybe emission or absorption. All right. Okay, this is the last topic, I think. Inductively coupled plasma and mass spectrometry. Two different techniques are combined. Okay, first, atomization is done by this inductively coupled plasma, and some atoms now ionized, yeah, and then enters the mass spectrometry. Okay, you will see the details of mass spectrometry in next chapter. The mass spectrometry determines the mass of ions, not neutral atom, cannot be detected by mass spectrometry. Okay, yeah. So ionization is needed in this case. So to couple this inductively coupled plasma and mass spectrometry, you have to uh, have have a means to to combine this together, and also that the atom the ionization method must be incorporated. Okay, let's look at this schematic diagram of this technique here. Well, from here, let's say from ICP here, here's a plasma, right? And then very little sample is introduced to this mass spectrometer here, okay? And then this a schema cone, right? This schema cone, you see this part is toward here, and then very little amount of here. Uh, Let me see, atoms, right? Now enters this schema cone, and then through this what the high voltage extraction lens, and then introduced to this what hexapole collision cell. Okay, here, okay, and uh, here on front and in the back there is a electrostatic collimator uh, here, but usually the mass spectrometry you need the vacuum, yeah, a small vacuum, and that this one a little bit this vacuum is a very high vacuum. Okay, yeah. So sampling is difficult because in you need extremely small amount of sample uh, to this mass spectrometry. Okay, so here this schema cone now remove almost all the samples, but it allows the very small amount of sample to be entered into enter to this now this part. Okay, well, so with this technique, part per trillion detection limit is possible. Anyway, let's see. Here, you make a vacuum here in this part, yeah, between the sampling cone and the schema cone. Yeah, the vacuum is pressure is 10 to minus 3 bar. Okay, this is not high vacuum, yeah? medium vacuum. And then here, from this schema cone and here this part, you also apply the vacuum. Okay, and then here let me see this uh, uh, this part, this is called the hexapole collision cell. In this cell I think the helium uh, is input, yeah, to this hexapole collision cell, and then with the helium, and then the particles from here, atoms now collide, and then some of them may be ionized. Okay, and then this part you apply the higher vacuum, yeah, the 10 to minus 5 bar. Okay, and then now this is one these parts are electrostatic collimator. Okay, this is ion optics. Okay? Collimation means to make the pin path straight. Okay, and then here is the deflection plate. Okay, by applying the potential. Okay, and then since the ions takes charge, and then ion pass not straight, but ion pass is bent. Okay, and then it passes through this one, this barrier, and it enters to this quadruple mass separator. Okay, this is a quadruple mass. This is a detector. Okay, here this is a quadruple. Okay, because it has 1, 2, 3, 4 poles. Okay, and you see the principle of this quadruple mass separator. And to operate this separator, you need in higher vacuum, okay, 10 to minus 9 bar. Okay, and then here atoms are separated, ions are separated. Yeah, here there are many ions now enter this quadruple mass separator, and then it's an exit, and then now exit ions are detected by this detector. Okay, yeah, this in that way, extremely low concentration of sample could be detected. How low? PPT, part per trillion. The million, part per million, part per billion. This out of 1 out of 10 to 9, and part per trillion is 1 out of 10 to 12. Okay, yeah. So this is extremely sensitive technique, but very very expensive. Okay. Solutions must be made from extremely pure water and trace metal grade, nitric acid in Teflon or polyethylene vessels protected from dust. In order to operate, this mass spectrometry, you need, very high quality, reagents. Okay, yeah. For example, the water, you need extremely pure water. Okay, and trace metal grade, this one, nitric acid. Okay, hmm? Contained in Teflon or polyethylene vessels. No, in this case, for this extremely pure, the solvent or reagent, you need, you cannot use the glassware. Okay, because from the glassware, some metal ions what is leached. Okay, to the solution. So in this case, you need Teflon or polyethylene vessels. Okay, protected from dust. Mm. So you have to exercise extreme care. Okay, to operate this one. Okay, and there is a interference called isobaric interference. Okay, this isobaric interference is the what by ions of a similar mass to charge ratio. Okay, for example, look at that. Now, since we are considering this coupled this technique, mass spectrometry. So the um, uh, the input species to mass spectrometry is ions, not atom. Okay, not neutral species. Neutral species cannot be detected by the mass spectrometry. Okay, to use this mass spectrometry, you have to ionize something. Okay, so here isobaric interference is the same mass to charge ratio. Okay, look at that. This argon oxide, right? Uh, just plus one charge. Okay, what's the mass? 40 plus 16 is 56. Okay, with the one monovalent positive ion. Okay. By the way, ionization makes usually mostly positive ions. Okay, not negative ions. Okay, and here what's the mass to charge ratio here? Okay, 56 divided by 1 is 56. Okay, and this one is ion. This ion species with the mass number 56. This is the same. You know, okay, and here this one argon dimer and mass to charge ratio is what 80. Okay, because it is 40 times 2. Okay, it's 80. Interferes this selenium, monovalent selenium, whose mass is 80. Yeah, this one. So with there's species that have the same mass to charge ratio, it's difficult to differentiate by this technique. Okay, Of course, if you have extremely, the extreme high resolution, mass spectrometer, and then you don't have to worry about that. But with this quadruple mass spectrometer, it is difficult to differentiate these species. Okay, that's the isobaric interference. Hmm? But how do we solve this problem? One solution is to use dynamic reaction cell instead of a collision cell, because the collision cell can reduce the isobaric, this collision cell cannot remove this isobaric interference, but dynamic reaction cell is good for removing isobaric interference. Okay, this is collision cell. Okay, in this collision cell, ions are formed. Okay. Okay, let's consider the principle of the dynamic reaction cell. Okay, dynamic reaction cell contains a reactive gas such as ammonia, methane, and nitrous oxide and carbon monoxide or oxygen molecules. Okay, and then how do these species remove this isobaric interference? Okay, here is an example. So if ammonia, molecule is there, ammonia gas is there. And for example, this argon, the ion, yeah, react with ammonia, and it makes an ammonia ion and argon, neutral argon gas. Okay, yeah. So this argon, this ion's effect is removed. Okay, and this one. And if argon carbon, this molecular ion is formed, and it reacts with ammonia, and it takes this positive charge, and then as a result, argon and carbon gas, atomic gas is formed. So this they are neutral species, so they don't interfere the measurement. Okay, and this one, likewise, it reacts with ammonia. Okay, all right. This is electron transfer. Okay, here, this electron over from ammonia now transport to this ion. Okay, and also proton transfer is possible. Look at that. This argon, this hydrogen, this molecular ion. Yeah, this proton from here transport from here to there. So as a result, ammonium ion is formed. Okay, I like that. This one, argon, nitrogen, hydrogen atom, ion. Now proton transport. Okay, transport. And this one, chlorine, the hydroxide ion. Now proton is transported to the ammonia molecule. As a result, it produces a neutral species. Okay, here is an example. This argon, carbon molecular ion interferes. Yeah, this chromium, whose mass number is 52, ion. Okay, this one is also mass number is 52. Okay, and also this one, chlorine hydroxide. Yeah, this is also mass number is 52. It they 1, 2, 3. This one interferes this one, and also this one. This is interfere with the chromium ion. Okay, this is mass number is 53, and this is 53. Okay, 35 plus 17 plus here hydrogen 1. Okay, so and then if you use a dynamic reaction cell, now ammonia, this one, react with this species. Okay, for example here, and then what, it makes this argon. Okay, neutral and carbon neutral. Okay, yeah, so it removes uh, the interference from argon and carbon. Okay, argon and carbon. So only the chromium ion, mm, is there. It can be detected by mass spectrometer. Okay, yeah, that's the principle. Okay, somehow it's very simple. Okay, very important. Okay, yeah, this is the end of this chapter 20, and here homework problems. You solve these problems and upload your answers. Okay.